Next we come to the binary eutectic systems. For binary eutectic systems, two metals or compounds are not mutually soluble in every proportions. Here in this figure we can see the copper-silver phase diagram, which is an example of binary eutectic system. In this phase diagram we can see the vertical axis in the left hand side denotes the 100% of pure copper, which has a melting point of 1083 degree centigrade. Similarly, the vertical axis in the right hand side denotes 100% of pure silver having a melting point of 960 degree centigrade. In the left hand side of the phase diagram, we can see a solid solution phase of alpha, which is actually a solid solution of silver in copper. This is because in the left hand side the amount of copper is more and hence it is the solvent, while the amount of silver is less and hence it acts as the solute. Similarly, in the right hand side of the phase diagram, we get the solid solution phase of beta, which is the solid solution of copper in silver, because the amount of silver is more and hence it is the solvent, while the amount of copper is less and hence it is the solute. For both these cases of alpha and beta, we can observe that there is a limit of solid solubility. In this case, it is 8% of silver in copper, and this solid solubility decreases with the decrease of temperature along the solver's line. So this phenomena is also present in the right hand side in case of the beta phase. That is, there is a limit of solubility of copper in silver, and this solid solubility decreases with the decrease of temperature. Now such a phenomena or process, that is, the solid solubility has an upper limit and the solid solubility decreases with the decrease of temperature. Such phenomena is an important requirement for precipitation strengthening process, which is one of the strengthening mechanisms. Now, in between the alpha and the liquid phase, we are getting liquid plus alpha phase. In between the liquid and beta phases, we get beta plus liquid phase. Here we get the uniform liquid phase, that is the liquid solution of copper and silver, and over here in between the alpha and beta phases, we get a combination of alpha plus beta phases. This particular line across the liquid phase is called the liquidous line. This line across the solid solution phase of alpha or beta is called the solidus line, whereas this particular line in between the alpha or the beta phase and the combination of alpha plus beta is called the solvus line. So these liquidus, solidus and solvus lines are also present in the right hand side of this phase diagram. Now over here we can get a horizontal line which we call it as the eutectic line or eutectic reaction isotherm. Now this line represents a particular temperature called the eutectic temperature. In this case it is 779 degree centigrade. Here we get a point called the eutectic point denoted by E. In this case, for copper silver phase diagram, the composition of the eutectic point is 71.9% of silver. Now let us come to the eutectic reaction. Here we can see that if we consider an overall alloy composition having the eutectic composition of 71.9% of silver, and if we cool down this alloy from the liquid phase, once it crosses the eutectic point at eutectic temperature of 779 degree centigrade, the entire liquid gets converted into two solid phases, that is alpha and beta, as per this equilibrium phase diagram. So a liquid phase of eutectic composition, when cooled down at eutectic temperature, it gets converted into two solid phases of alpha and beta. This particular reaction is called the eutectic reaction. For this reaction, from the lever rule, we can separately evaluate the compositions of alpha and beta phases. Here we can get the composition of alpha phase is 8% of silver, which we can get from this intersection point, whereas the composition of the beta phase is 91.2% of silver, which we can calculate from this intersection point. Now, as described in previous sections, the lever rule is equally applied in the regions of two phases in such systems as well. Now, the alloy on the left hand side of the eutectic composition in a binary phase diagram is known as the hypoeutectic, whereas on the right hand side of the eutectic point is called hypereutectic. So these are the basics of the binary eutectic phase diagram and the eutectic reaction. Here we can see that the late teen phase diagram is another example of a binary eutectic system. Here the melting point of pure lead is 327 degrees centigrade, while for pure 100% tin the melting point is 232 degrees centigrade. Alpha is the uniform solid solution of tin in lead, while beta denotes the solid solution of lead in tin. Similar to the previous phase diagram, here we get the uniform liquid phase, that is the liquid solution of lead and tin. In between the liquid and alpha phase, we get alpha plus liquid phase, and in between the liquid and beta phase, we get beta plus liquid phase. Here, in between the alpha and beta phases, we get a combination of alpha plus beta phases. Here, similar to the previous phase diagram, we can see that the solid solubility of tin in lead has an upper limit of 18.3% of tin, which decreases with the decrease of temperature. And this phenomena is also present for the beta phase. Here, the eutectic temperature stands 183 degrees centigrade, while at the eutectic point the composition is 61.9% of tin. So, if we consider the eutectic reaction, we can see that whenever an alloy composition of the eutectic composition 61.9% of tin is cooled down from the liquid phase at the eutectic temperature of 183 degree centigrade, the liquid phase will be converted into the two solid phases of alpha and beta, which is revealed in this equilibrium phase diagram. So, similar to the previous phase diagram, as per the lever rule, the composition of alpha is 18.3% of tin, which we get from this intersection point, while beta has a composition of 97.8% of tin, which we can evaluate from this particular intersection point. Thus, this late tin phase diagram is another example of the binary eutectic system, and this is another example of the eutectic reaction. So, the lever rule and its application is valid for any two-phase region for any type of phase diagram. Let us now study about few applications of binary eutectic systems. Here in this figure we find the phase diagram of water and sodium chloride, that is salt. Now in the first part of the problem we will explain about how spreading of salt on ice, that is at a temperature below 0 degree centigrade, can cause the ice to melt. Now here in this phase diagram, we find the y-axis is represented by temperature, while the x-axis is represented by the increasing concentration of sodium chloride, that is salt. Therefore, the vertical axis in the left hand side denotes the 0% of sodium chloride, that is 100% of water which has a melting point of 0 degree centigrade. Here we find a phase of liquid brine solution plus ice, whereas in the right hand side we find the phase of liquid brine solution plus salt. In between we find the phase of only liquid brine solution, and at the bottom of the phase diagram we find the phase of ice plus salt. Now if we consider any arbitrary temperature below 0 degree centigrade, say for example minus 10 degree centigrade, we can find that with increasing concentration of salt, we enter from the phase of liquid brine plus ice to the phase of liquid brine only. That means the ice is melted. Now this temperature at which the ice will melt due to the addition of salt is decreasing with the increasing concentration of salt, which is revealed by this line. In the second part of the problem, we have to evaluate at what temperature is salt no longer useful in causing ice to melt. Here we can see that below certain temperature, under minus 20 degree centigrade, everything is ice plus salt irrespective of the salt concentration. So we cannot find the liquid brine solution. So below this particular temperature, the salt is no longer useful in causing ice to melt. So this explains one of the applications of binary eutectic system. Binary eutectic systems are also applied in metal joining processes like soldering. Firstly, let us know about what are solders. Solders are the metallic alloys that are used to bond or join two or more components, usually the other metallic alloys. They are used extensively in the electronic industry to physically hold assemblies together. Moreover, they must allow expansion and contraction of the various components. They must transmit electrical signals, and they should dissipate any heat that is generated. Now the bonding action is accomplished by melting the soldered material, allowing it to flow among and make contact with the components to be joined, which usually do not melt, and finally upon solidification forming a physical bond with all of these components. Frequently, low melting temperature alloys are prepared having near eutectic compositions. A familiar example is the 60-40 solder, which contains 60 weight% of tin and 40 weight% of lead. In this figure, we can see a lead-tin phase diagram where the eutectic composition is 61.9% of tin and eutectic temperature is 183 degrees centigrade. So, according to this lead-tin phase diagram, an alloy of this composition, that is 60 weight% of tin and 40 weight% of lead, is very near to this eutectic composition of 61.9% of tin. It is completely molten at about 183 degrees centigrade, the lowest temperature which is possible with the existence of a liquid phase at equilibrium for this lead-tin system, which is revealed from this phase diagram. Now this makes the material specially attractive as a low temperature solder, since it is easily melted, reliable and also inexpensive. This is why the alloy is often called as the eutectic lead-tin solder. Regarding the lead-tin solder, it is important to remember that lead is a mildly toxic metal and there is serious concern about the environmental impact of discarded lead-containing products, which can leach into groundwater from landfills or even pollute the air. Now this has encouraged the development of lead-free solders, which must have relatively low melting temperatures or temperature ranges. Some of these are actually ternary alloys, that is composed of three metals, for example tin, silver, copper and tin, silver, bismuth solders. Melting temperatures or temperature ranges are important in the development and selection of these new solder alloys. Such information is available from their respective phase diagrams. For example, here we can see a tin bismuth phase diagram where the eutectic composition is 57% of bismuth and the eutectic temperature is 139 degrees centigrade, which are actually the composition and melting temperature of this bismuth tin solder. Thus, the binary eutectic systems are extensively applied for making of different solder alloys. In the previous section, we have studied about the eutectic reaction. Now, let us learn about the different other phase reactions. In the eutectic reaction, one liquid phase, that is L, on cooling is converted into two solid phases of alpha and beta, which we have already studied in the previous section. Next is the eutectoid or eutectic-like reaction, where one solid phase, that is gamma, on cooling is converted into two solid phases of alpha and beta. Next, for the peritectic reaction, one liquid phase, that is L, and another solid phase, that is alpha, on cooling is converted into a single solid phase of beta. Next is the peritectoid reaction, where the two solid phases of alpha and gamma on cooling is converted into a single solid phase of beta. Next, it comes the monotectic phase reaction, where a single liquid phase, that is L1 on cooling, is converted into a solid phase of alpha and another liquid phase, that is L2. Lastly, for the syntectic phase reaction, two immiscible liquid phases, that is L1 and L2 on cooling, is converted into a solid phase of beta. So these are the different phase reactions which are available. At this point of time, it is important to learn about the Gibbs phase rule. With respect to the phase diagram, Gibbs phase rule represents a criteria for the number of phases that will coexist within a system at equilibrium, and it is expressed by the simple equation of P plus F equals to C plus N, where P is the number of phases present, the parameter F is the number of degrees of freedom or the number of externally controlled variables, example like temperature, pressure, composition, which must be specified to completely define the state of the system. If expressed another way, F is actually the number of these variables that can be changed independently without altering the number of phases that coexist at equilibrium. The parameter C in this equation represents the number of components in the system. Now components are normally elements or stable compounds, and in case of phase diagrams, components are the materials at the two extremities of the horizontal compositional axis. Finally, N is the number of non-compositional variables, example like temperature and pressure. Thus, this Gibbs phase rule is valid and applicable at any point of a phase diagram. Let us now study about the iron-carbon phase diagram. The iron-carbon phase diagram is one of the most important diagram of any metallic system. Here in this figure we can see the iron-carbon phase diagram, where the y-axis is represented by the temperature scale, while the x-axis is represented by the increasing composition or weight percent of carbon. Now, the vertical axis in the left hand side denotes the zero weight percent of carbon, that is pure iron, while the vertical axis in the right hand side denotes a particular phase called cementite, which is actually a chemical compound of Fe3C having the carbon weight percent of 6.7. Therefore, as a matter of fact, the iron carbon phase diagram should be called the iron Fe3C, that is cementite metastable diagram, since in real practice the nucleation of stable equilibrium graphite, that is pure carbon, is very much difficult. Let us now talk about the different phases present in the iron carbon phase diagram. In the previous section, we have studied about the cooling curve of pure iron showing polymorphism or different crystal structures. Now, when carbon forms the interstitial solid solution with the different forms of pure iron, we get the different phases at different temperature ranges in the iron carbon phase diagram. For example, in the cooling curve of pure iron, below 910 degrees centigrade, we get the alpha iron showing BCC crystal structure. So, when carbon forms the interstitial solid solution with alpha iron, we get the ferrite phase in the iron carbon phase diagram. Similarly, below 1400 degrees centigrade, in the cooling curve of pure iron, we get the gamma iron having FCC crystal structure. When carbon forms the interstitial solid solution with gamma iron, we get the austenite phase in the iron carbon phase diagram. Similarly, above 1400 degrees centigrade up to 1540 degrees centigrade, that is the melting point of pure iron, we get the delta iron having BCC crystal structure. So, when carbon forms the interstitial solid solution with the delta iron, we get the delta phase in the iron carbon phase diagram. Thus, as and when the carbon forms the interstitial solid solution with the different forms of pure iron, we get the different phases at different temperature ranges in the iron carbon phase diagram. And since the vertical axis in the iron carbon phase diagram represents the pure iron, over here we get the same temperature ranges for different phases, that is 912 degrees centigrade, 1400 degrees centigrade and 1538 degrees centigrade, similar to the temperature ranges in the cooling curve of pure iron. To come with the next phases, in between the ferrite phase and the cementite phase, we get the combination of ferrite and cementite, which is actually the layers of ferrite and cementite termed as pearlite phase. Here we get the uniform liquid phase. In between the austenite and liquid phase, we get the austenite plus liquid phase, and in between the austenite and cementite phase, we get the austenite plus cementite phase. So, these are the different phases which are present in the iron carbon phase diagram. Next, we talk about the steel and the cast iron. The iron carbon phase diagram may be divided into two portions, the left hand side pertaining to steels, while the right hand side belongs to cast iron. It is obvious that melting point of cast iron is far lower temperature than that of steels. Now, below approximately 1.8 weight% of carbon, we call it as steel, while with higher than 1.8 weight% of carbon, we call it as cast iron. Now, with the increasing weight% of carbon, the steel becomes brittle or the ductility decreases. That is why the cast iron is much more brittle compared to the steel, because the cast iron has the higher percentage of carbon compared to steels. Moreover, here the cementite phase or Fe3C is itself a brittle phase. Let us now talk about the few relevant points and temperatures in iron-carbon phase diagram. Firstly, the maximum solubility of carbon in the ferrite or alpha iron is 0.022%, which is denoted by this point, while the maximum solubility of carbon in the austenite or gamma iron is about 2%. Over here we get the eutectic point having the eutectic composition of 4.3 weight% and eutectic temperature of 1147 degree centigrade. Over here the liquid phase on cooling get transformed into two solid phases of austenite plus cementite. Next, here we get the eutectoid point having the eutectoid composition of 0.76 or 0.77% of carbon and the eutectoid temperature of 727 degree centigrade. So over here the austenite phase on cooling get transformed into the two solid phases of ferrite plus cementite. In other words, the austenite transforms into an eutectoid mixture of ferrite plus cementite known as pearlite. Steels with carbon less than the eutectoid composition, that is in the left hand side of this eutectoid point, is known as hypoeutectoid steels, and those greater than the eutectoid composition, that is in the right hand side of the eutectoid point, is known as hypereutectoid steels. In hypoeutectoid steels, we have primarily ferrite plus pearlite phase at room temperature, whereas for the hypereutectoid steels, they are cementite and pearlite. Now, the cementite is noticed over here as a network around the pearlite colonies. Since cementite is a hard and brittle compound, so the hypereutectoid steels have lower ductilities. So, since in the hypereutectoid steel have the composition of pearlite plus cementite, and for the hypoeutectoid steel the composition is pearlite plus ferrite, and cementite is a brittle phase compared to the ferrite phase, so the hypereutectoid steel is a brittle one compared to the hypoeutectoid steel. So these are the different relevant and significant features of the iron-carbon phase diagram. As mentioned in the previous section, the iron-carbon phase diagram illustrates three types of phase reactions. The first one is a eutectic reaction at composition of 4.3 weight% of carbon and eutectic temperature of 1147 degree centigrade, where the liquid phase on cooling get transformed into two solid phases of austenite plus cementite. The second phase reaction is a eutectoid reaction at composition of 0.76 or 0.77 weight percent of carbon and eutectoid temperature of 727 degree centigrade, where the austenite phase of eutectoid composition 0.76 weight percent of carbon on cooling get transformed into two solid phases of ferrite plus cementite. Now, after the eutectoid reaction, by means of lever rule, we get the compositions of alpha as 0.022 weight percent of carbon and the composition of cementite to be 6.7 weight percent of carbon. So we get separate compositions of ferrite and cementite phases by means of lever rule. The third phase reaction is the peritectic reaction at 1493 degree centigrade, where from the liquid plus delta phase on cooling we get the single solid phase of austenite. So these are the few significant phase reactions which are revealed in an iron carbon phase diagram. The figures over here reveal the variations in mechanical properties with respect to the carbon content in case of plain carbon steels having microstructures consisting of fine pearlite phase. In the first figure, we can see the variations in yield and tensile strength as well as the Brinell hardness with respect to the carbon concentration, where we can see that strength and hardness increase with increase in carbon content. In the second figure, we can see the variations in ductility in terms of percentage elongation and percentage reduction in area, as well as the Izod impact energy with respect to the carbon concentration, where we can see that opposite to the trend in strength and hardness, ductility and toughness decrease with increase in carbon content. So this is about the variation in mechanical properties with respect to the carbon content in a steel.